All right. Let me get started. Heavenly Father, we thank you for this day. I thank you again for your creation, that we can study it and enjoy it and understand it. Help us to learn a little bit more about your creation today. Help us to prepare for the test Wednesday, and that you just be glorified in whatever we do this day, Lord. In your name I pray, Lord Jesus. Amen. Okay, so I see I have your mission 2. Very good. I will hopefully get that back to you next class. I will post a solution here, hopefully before I leave today. I have it solved already. We're going to look at it now. So now if you, so just a point of order, if you're, in a group and you have not, contributed to your group, and your group has let me know that you are doing nothing, then you do not earn points. You earn 0 points. But the good news is that I will let you get points from the test in place of those points that you did not earn on said mission. So, general point of order, if you have a group member who flakes out on you and will not answer your emails, etc., who doesn't work with you, you let me know and I give them no points. Now, of course, if I give you a 0 in this kind of situation and you're like, no, I did contribute to it, well then we'll have to convene a court of team mission, and I'll have to find a judge to arbitrate over this dispute, and let's just not have that happen, Sprano. Let's just... Nevertheless, of course, that team will cease to exist after that time, and so forth. But anyway, these things are not going to happen. So let us begin. So this is problem. So first of all, criticism I have of my missions. I neglected to put anything about conductors on these. Do not construe that to mean that there aren't conductors on the test. There are very likely going to be a problem with the charged conductor on the test. We did work examples like that in class. That is part of the material. Point number 1. Point number 2 is we can have variable density. We have worked problems in class with variable density. It is likely there's at least one variable density problem on the test. So 2 comments. That said, let me get into it here. So here we're trying to find the electric field at radius r inside a spherical shell. So I've just shaded the part where there's charge enclosed, right? And so to figure out the charge density, I take the net charge, which is q, divided by the net volume of the shell, which is 4/3 pi b cubed minus a cubed. All right? I take that and I multiply it by the volume enclosed, which in this case would be 4/3 pi r cubed minus a cubed. That gives me this. Now, as a quick check, if I put r equals to a, I get 0. That makes sense, right? There's 0 charge enclosed if I'm on the inner radius. And as I take the limit as, r goes to b, I get q, which also makes sense because the net charge is q. So this formula checks in those two cases. And then you just, Gauss's law, right? So Gauss's law to the sphere, the spherical symmetry gives me that the charge enclosed divided by epsilon naught is the flux, but the flux is the electric field times 4 pi r squared. And so then what does that give me? Well, that gives me this equation here, which then I solve for E, and I get this, right? And I think that makes sense because if we put in r equals to a, we get 0, which is what I expect. The electric field inside the inner radius would be 0 because there's no charge enclosed and there's a spherical symmetry, right? So we have 0 electric field in there. This one's radially outward. Like I said, E equals 0 for radius less than a. And then once you're outside radius b, well, you got the whole charge enclosed. So we're just going to be back to the Coulomb field out there. All right? So any questions? Okay, well, we go on here. This one, again, as I told you before, I don't expect you to do this calculus on the test, right? This was a problem in the homework that's not on the test. I told you that explicitly. And I also pretty much worked this out, right? with it slightly different, but very similar electric field. But here's the details. If you want to actually calculate the infinitesimal area element, you take the cross product of the partial velocities, and then you take the dot product of this this guy with the electric field evaluated, and a lot of stuff is 0 in this particular calculation. The radius is 1 because we're given it's a unit sphere. And so this all works down to 4/3 pi. And on the flip side, the way you guys almost all of you, I'm sure, I strongly doubt that I will see these details in any solution, right? Because I gave you license to do this instead, right? Which is to use the divergence theorem, which trades the flux of the electric field for the triple integral, the volume integral of the divergence, which in this case is 1. So it's 4/3 pi because that's a unit sphere, and so we get the charge enclosed is 4 pi epsilon naught over 3. So again, to be clear, I do not require you to know the divergence theorem, as calculus 3 is not a prerequisite. Although I do think that this posture in classes that we don't talk about things that are in prerequisites, it doesn't really make sense, to be honest. Because many of you have had calculus 3, but you also don't know these things. So what's the difference? Sorry, but you know. And I'm not talking about anybody in particular. I'm talking about most Calc 3 students don't learn the divergence theorem. Not really in that class. So it would actually be good for us to teach it here again so that you at least see it twice. All right, anyway, I got that out of my system. Let's go on here. So this one, you got to charge Q1, which I put in the blue part, and you got to charge Q2, which I put in the red part, right? And the question is, what's the electric field again? So as a point of order, this is the density in the first region, all right? The charge per unit volume. And this is the density in the second region because I've got Q2 smeared out over the volume of this, you know, spherical shell. And so the charge enclosed for a radius R1, which is inside A, and I put an R1 and an R2 here because I didn't want to draw two pictures. That's it. I'm just lazy. So I put R1 and R2 both on the same picture. So for, stop the blinking, R1 less than A. Hey, listen to me. It's an illusion. It's just biding its time. It's going to blink again. Watch it. So Q enclosed over epsilon naught. I told you. So rho 1 times the volume. In the inside, it's just a solid chunk of charge, right? So the volume of the inner Gaussian sphere is simply 4/3 pi R1 cubed, and spherical symmetry, I still have 4 pi R1 squared times E, so I solve for E there. And that gives me what I have right there. And again, sorry about the blinking. It'll do what it does. And then I don't like R1 for my answer, so I changed the R1 to R, and there you go. This is the formula for the electric field on the inside. It's radially outward. That's the formula. We worked this out in class, right? Like we worked the uniformly charged sphere in class. This is the same answer we got there. It's linear from the inside, and it goes to the Coulomb field at the edge, right? But what's new here is that there's charge outside the inner charge, right? So when we reach the case of R2, there's a little bit more to think through. See now, when you have R2 larger than A, you're automatically enclosing the inner charge, right? So the net enclosed charge is Q1 plus whatever portion of Q2 that you have, which would be this. And again, there's spherical symmetry, so we have 4 pi R2 squared E, solve for E, change my R2 to R, there's the answer. And as a point of order, it does reduce to what you'd like, right? Which is the Coulomb field. When you put, let's see here, if I put R equals to A, this just drops back down to Q1 over 4 pi epsilon naught A squared, which is the edge case of the inside one. And in the limit that we get to B, we just get Q1 plus Q2, which speaks to the outside case, right? Which is just the Coulomb field. We've got a whole of Q1 plus Q2 enclosed. So we just drop back to the Coulomb field for R greater than B. Yeah.
How do we know that it's R less than B and not R is less than or equal to B for that case?
Oh, I just chose to make that my case.
Cool.
Yeah. So I want to address every possibility, and the reason I didn't put equals there is because then I feel obligated to discuss a limit, because technically speaking, if you must know, the formula there is not defined. I'd have division by 0 if I included equality there. Yeah. Not that I'm taking points off any year, like you divided by 0 in this case, ha ha, lawyer, I'll take 30% of your points. No. I don't need to do that. I have other ways of taking your points. So I don't want to have any, nothing would delight me more than when I assign grades at the end of this class. I would just like A, like the Fonz, you know, just like A. Sorry, you guys know what the Fonz is, but some of you do. It's okay. Some things are better left forgotten. But I would love to have to go to talk to the dean. James, why have you given 100% A's to this Physics 232 class? I'd be like, they're just all that good. Like that would be, I would love to have that conversation. Nothing would delight me more. It would make my grading very boring. But I'm okay with that. I don't need exciting grading. Don't give me exciting grading. I like grading to be very boring. Same answer, same answer, same answer, same right answer, right answer, right answer. So, right. I'm not, this is not an online class. I'm not saying you should just copy the answer. So, oh, oops. Yeah, yeah. So anyway, if we think about this cylinder here, if we think about the cylinder here, we're given that the flux is 3.0 Newton meter squared per coulomb. It goes across the cylinder of radius 5 centimeters. And the length is 30 centimeters. It encircles a long wire placed at the center of the cylinder. What is the charge per unit length in the wire? So this is kind of a play on an in-class example where we worked out the electric field was lambda over 2 pi epsilon naught times r, where r is the distance from the wire. But we can just apply Gauss's law here to the cylinder. The charge enclosed would be lambda times L. We know it's a uniform charge because of the problem's setup. And we know that the flux is 2 pi RLE, but none of that matters because we're told the flux is what? This. So like the R is irrelevant here, yeah? Which is kind of funny. So I get lambda L over epsilon naught equals to this. It's always a good point of order to put some unnecessary numbers on a physics test to make sure people know what they're doing. It's sometimes very informative because people who don't know what they're doing will just take the numbers and use them. Surely a physics professor wouldn't give you a number that you don't need to use on a test. Oh no, we do that. That's one of our signature moves. So anyway, I digress. So charge enclosed over epsilon naught is that. I solve for lambda, and yeah, that's what I got. Did you guys get that? Yeah. Okay. Good. I'm sorry. I should have picked different dimensions so you felt like you did more. I know it just seems like we rescaled the permittivity constant, but you know, yeah. So problem 11 is a twist. I'm sorry my picture is misleading. My picture makes it look kind of like the charge is at the corner. That's not what I mean here. It's just perspective. It's not quite the right picture. I don't know. I do mean that the charge is at the middle of the big box, all right? Okay? So like the box is, like the cube is going from minus L to L in both X, Y, and Z, right? So the charge is at the origin, which is smack dab in the middle, which means that the flux through any face has to be the same as the flux through any other face, and hence through any half face as well. This is a half face. There are 12 half faces, therefore 1/12 of the total flux must be going through that. And so I do Q over 12 epsilon naught. That's the flux through that face. This is a kind of a twist on the homework. We did an example in class where we worked out to 1/24. I would say this is somewhat related to that example. There are like a dozen different versions of this problem, you know, that you'll see. It does make a nice test question because it doesn't require like a lot of calculation. So, and then this one, I kind of more or less told you guys how to do this last class. My apologies. I think the problem statement here is a little bit misleading, as I was trying to indicate last class. Is like, you really should use superposition in two applications of Gauss's law. Like Gauss's law derives that the electric field is the charge density divided by 2 epsilon naught for a charged plane, right? I do that for both planes. But the one is sigma 1 over 2 epsilon naught. The other one has twice the charge. Sigma 2 is 2 sigma 1. So you end up with like sigma 1 over epsilon naught for the electric field of the second plane. And as such, we get E1 is, sigma 1 over 2 epsilon naught away from the Z1 plane. E2 is actually sigma 1 over epsilon naught away from the Z2 plane. And as you can see from the field lines, they line up on the top. They're opposite directions in the middle, and they're both in agreement downward in the last. So, I mean, how do you want to write that? So there's various ways you could say this. No one probably disagrees about part A. 3 sigma 1 over 2 epsilon naught up, right? There's different ways you could phrase your answer in the middle case. I say minus 2 sigma 1 over 2 epsilon naught up, but a minus up is a down, right? So equivalently, I could say sigma 1 over 2 epsilon naught down. Now, if you had written minus sigma 1 over 2 epsilon naught down, I'm not going to take points off here. I know what you meant, but technically, yeah, So if I was smarter, the way to avoid quibbling over up, down, plus, minus is simply to ask for the magnitude of the electric field. If I do that, then I can just take points off if you put a minus. Unambiguously. That's a less, there's nothing to argue about there. If I ask you for a magnitude and you give me a negative, then something's wrong with that, yeah. Anyway, so that's it. Any questions? So let me go back here to mission 1 just briefly. Remember mission 1? We looked at this the other day. Just to remind you, this is what mission 1 was about. We asked what the electric field was at a point due to a charge, right? And we talked about how if you use the Coulomb field, kq over r cubed r vector, that's a nice way to get the formula for the electric field that points away from that positive charge at 2, 3 at the field point minus 2, 1, right? So you do need to know how to set up the electric field due to point charge or several point charges, right? Use superposition, find the net electric field at the point. So we did a problem like that before, remember that? Magnitude and direction still matters. You got to think through it. If we're electric fields pointing in the third quadrant, you just can't use the inverse tangent of the ratio of y over x. You got to think through the standard angle business. This one's 206.6. Units for electric field are typically newtons per coulomb, right? We've seen that a bunch of times. There was this problem. Let's see here. Trying to think of anything else I want to talk about in here. Don't be frightened by this problem if I give it. Find the electric field at x comma y due to a charge at 1, 2, 3 and minus 1, 0, 4, right? That's not a bad problem. It's just you write down the Coulomb field and add them, and that's what it is. It's not, right? It's just here we got a variable point. Let's see here. What else can I tell you? I might put some parameters. If I was asked this again, I might use like some parameters so that we wouldn't be like violating dimensionality on the test. So the way I would do that would be do something like give you the point LLL, or maybe L, 2L, 3L, right? Where L is whatever it is. It's like some dimensional constant. If I did that, then we wouldn't have any kind of dimensional, what's the word? There would be no dimensional sins in my formula. As it stands, maybe don't show the other physics professors this. I might get in trouble. Don't tell Dr. Buderas for sure. Will there be integration on this test? Yeah, there's definitely going to be integration on this test. Integration is a big part of this course. This is calculus-based physics, so calculus is part of it. The only calculus we've done so far has been integration in terms of like either calculating the charge enclosed by integrating a variable density. We did a problem like that. Or by calculating the net electric field by adding up the electric field from each little bit. right? Which actually is a vector integral, to be fussy. But you know, I would, if I were you, I would review the integral problems we've done in here. We did this one, right? What's the other one we did? In class, right? Remember when we did in class, we had like a horizontal line segment, and then we asked what the electric field was, and do that whole distribution, like over here or over there. So we had to add up the electric field from each little piece to find the net electric field. That we did one of those like that. So, you know, any of the integrals that have come up in the problems, either, you know, in class or in the homework or in the problem sessions, these are all fair game. Like this one, for example, the integral of dy over x squared plus y squared to the 3/2 is an integral you should know, partly because you've already had calculus 2, so this is an integral you know, and partly because I'm talking about it right now. But yeah, so that one's actually not bad. Professor Dromby was asking me about this earlier today, which is kind of funny. This same one came up in her homework for a radically different problem, like a totally different problem. She has this problem about like finding the flux of a spherical charge distribution through a cylinder. That, I haven't done that to you guys yet. Do you want to cover it right now? No, that's the right answer. That's the right answer. So, yeah. There's apparently a mastering physics problem that's got that. It works out to this same integral, as it turns out. It's kind of funny. You do still need to know physics 1, right? If we talk about the electric force, if that's the net force, it's equal to the mass times acceleration. And if the electric field's constant, then that would mean it's a constant acceleration problem, right? On the other hand, if the electric field's variable, then you'd have a variable acceleration. How do you solve a problem like that? If I have an acceleration which is not constant but depends on position, how do I solve that? Integration, right? I think I pretty much would need to use the v dv dx trick. You know, if I had the electric field was a function of x, and I knew that that made the acceleration a function of x. Well, the acceleration, remember, is, so it would have to be one-dimensional pretty much, but the acceleration is like dv dt, right? But we can trade that out for dx dt, dv dx, which of course is v dv dx, right? So if I had that was equal to, you know, mass times v dv dx is equal to, say, q times the electric field, right? If that electric field was a function of x, I could find the velocity as a function of x if I could integrate that equation, right? How would you do that? Well, you learned in calculus 2 how to do separation of variables. So you could solve that problem ostensibly, if such a thing was to happen to you. But there's other integrations to talk about, right? Like one I just talked about, like charge distribution or variable density. Let's see here, anything else I should tell you guys about? You know, where is the electric field 0? Find the equilibrium position between two charge problem. There's a lot of different quirks and features to this problem. There's a lot of interesting stuff that can happen here. I would encourage you, if you haven't already, to watch the problem session where I work this out in general. There's an interesting calculation we did there, but yeah. Anyway, I'm gonna shut up. Are there any questions? You guys, any questions? Yes, no, maybe so.
I have sort of a random question about problem 10.
A random question. Problem, is it problem 10? Is that the next one?
Yeah, that's okay.
Go for it.
So if you're looking at that one, you can say E is k over r squared.
Whoa, wait a minute. You excuse me. You could say E is what?
Just kq over r squared, r hat, and then you can also say.
Hold on a second here. So you said E is kq over r squared r hat, and
right, just the regular equation, and then you can also set that equal to the density times L over E naught then A.
But
And
why?
then if you solve for,
But hold on a second. How could I say E is KQ over R squared R hat? Like, there's a context to that equation. I don't think I can say that here.
okay.
Because this
That
is,
would make sense, because then if you solve for the density, which I was looking at randomly, it turns out to Q over 2R, and then it's dependent on the radius.
yeah,
Which is
no.
why I just thought that was strange.
Right.
But if that would answer that question.
Yeah, so it's almost like if you have a very long line charge, you can just squash the dimension of the axis, and it's as if the flux just depends, like spreads out in 2 dimensions, which is why we get a 1 over r dependence on the electric field, as compared to the 1 over r squared dependence for the Coulomb field, where it spreads out in all 3 dimensions. Like, in some sense, the really long line charge, all of the electric fields which are sort of perpendicular to the line of the charge, they're all canceling out with each other. So that part of the flux just kind of like kills itself off, and it just leaves you with the radially outward part, which ends up reciprocally dropping as r. But the reason the calculation doesn't make sense is I can't say this here, and you're like,
That does make sense.
yeah, that's for a point charge at the origin.
Right.
Good question. Other questions? So you're allowed a 3x5 note card, right? You can write on 2 sides of it, not 3. I've had trouble in the past with people pulling them apart and trying to make it into a 4-sided note card. It's been done. So I have to just 2 sides. You can write whatever you want on it, right? If you want to print it in size 6 font, I don't care. Like, whatever. You are allowed to bring a magnifying glass. I will allow it. Let's go. Yes. And you are allowed a calculator, right? So, yeah. I think I would allow a TI-84 because I don't think I said otherwise. So, yeah. In my heart, I just want it to be a scientific non-graphing calculator, but I think that would be something I should have announced day one. I don't think I did. So.
Is it?
The one calculator which is not fine is this one. So no on the phone calculator, obviously. This is not allowed, right?
Is
So
it one-sided or both?
the calculator?
No. The index card.
Oh, the index card. Yes, you can use both sides of the index card, yeah. Other questions? Any questions about the recommended homework? I didn't get to work all of them, so yeah.
Do you have any like book problems or sets that you really recommend to help prepare?
I recommended 20 problems in the announcements, so those ones, yeah.
Just redo all of it, just kind of go through.
I would suggest those, yeah. But I would also suggest if we did an example in class, like that is something I'm thinking about, So I'd say examples we did in class are typical. Certainly, like I said, there should be a problem about electric field with a charged conductor. We looked at an example. The main idea there was the electric field inside is 0, and we have to think through Gauss's law, right? So again, my apologies. I didn't put one of those on your mission, but I'll make up for it by putting it on the test. So, yeah. So I guess that's a promise. I have to have a charged conductor problem on the test, at least one. What's the simplest charged conductor problem? How about this? I've got an infinite plane, a slab, right? Metal, right? And I've got a surface charge. It has to be uniform because that's how they work, right? What's the electric field due to that? So we already, as we have discussed, the electric field is equal to 0 down here. And then if I just take any old, Gaussian cylinder that cuts through here, well, my Q enclosed is sigma A, and the flux is EA, because the electric field lines have to do what? They have to go perpendicular to the plane. So I just get Q enclosed over epsilon naught equals to the flux through the cylinder, which in this case gives me sigma A over epsilon naught equals to EA, which simply gives me that the electric field is sigma over epsilon naught. So you notice the difference upwards, right? You notice the difference here between the charged sheet and the conducting plane, right? All of the flux has to go up because none of it can go into the conducting plane. So instead of having half, you get the whole flux, namely, sigma over epsilon there. And, and of course there are other things we could talk about. Yeah. Yes, sir.
Will there be like measures on the test? I know it sounds like, or is it just like right now?
For example, we might put a charge of Q uniformly distributed on the inner sphere, say of radius r. And then I give you that there is a metal, and it's charged, net charge 3Q. There's a 1 here. There's a 3 here. So yes, I mean, I cannot do examples without numbers, absolutely. And so then the question, of course, for this problem would be, find the electric field in the different regions. So if this Q on the inside is like uniformly distributed, we're back to this first problem of the, the homework. We got to look at our radius. We're going to have linear dependence from 0, just like part 1 of the homework. Then we have the Coulomb field between the inner charge thing and the metal. We know that the electric field is equal to 0 here. And what else do we know? Because the electric field's 0 into here, we must have a charge of minus Q on the inside, right? There has to be a minus Q on the inside surface, because when we make the Gaussian sphere inside the conductor, the net charge enclosed must be 0, otherwise we'd have an electric field by the spherical symmetry, but we don't. So therefore there has to be a minus Q on the inside. I told you that the net charge was 3Q, which puts a 4Q out here, right, on the edge. So the electric field, if we're at radius bigger than, let me say, B, for radius bigger than B, what's the field? Well, it's just the Coulomb field, right? And what's the charge? So we'd have what? We'd have Q plus 3Q. We'd have a 4Q over 4 pi epsilon naught r squared outward, radially outward. Sorry, my handwriting is degenerating. This is for r greater than V. And for this particular problem, I would not be allowed to ask what the electric field was at r equals to B or at r equals 2. I didn't give it a name yet, but let me call it A. Right? At radius A and radius B, there's a concentration of charge on the surface. Therefore, I can't actually ask what the electric field is at those 2 points. But I can tell you it's 0 inside the metal. It's like a Coulomb field that drops off outside the charge. It's linear from 0 up to the Coulomb field inside the uniform charge in the middle. And then outside, it's that. Because the net charge enclosed would be, Q minus Q plus 4Q. Yeah, you do need to know your micros and your nanos and your millis and your megas and your go down the rest. Of course, if you ask me nicely, I might tell you. But but what if I told you wrong? I mean, I'm kind of bad with numbers, right? We've demonstrated that in the problem sessions if you've been there. I really should have just assigned you even problems so that we can't tell if I'm right or wrong, Like, well, did it with authority, it must be right, right? So the test, I'll probably try to have like a few easy problems that are kind of like supposed to be quick. And then I'll have, a few problems that take a little bit longer, and you'll have like a whole page to solve them. I do need to see steps. Like I need you to see, I'm using this Gaussian cylinder, I'm using this Gaussian sphere. Like a little sentence telling me what you're doing would be super helpful. Things like that. I haven't always written those sentences on the board in here, but I always say them, But as long as you draw a picture, I probably can tell what you're doing. But, your goal is to convince me you know what you're doing. So work towards that goal, right? So anyway, that's all I got. Yep. Oh, enough? Yeah. That's what I always say. But oh, well, time is, the whole point of a test is time pressure. So there will not be enough time. There will not be enough time, no. Unless you know what you're doing. And then there'll be enough time. So, I mean, it depends. Is there enough time? I don't know. There could be enough time. That's a personal question. I don't know. Maybe you're tired, right? Because you stayed up all night studying. Don't do that, right? I don't know. Unless you don't know stuff and then stay up all night to study it, I guess. There's a balance to be struck here. I know that procrastinating the studying till the day before is desirable, indeed applauded by engineers. So by all means, for the purpose of maintaining your credibility with your peers, do not study today, wait till tomorrow, later tomorrow, document evidence of this, share it with your friends to increase your street cred in this class, as I understand it. Or not do that, maybe just study now, I don't know. But it's going to be okay. It's going to be like the stuff we've already done. I hope you guys do well. See you Wednesday.